Welcome to the lesson on polynomials. At the end of the lesson, we will be able to explain polynomial and its types, explain zeros of a polynomial and its relation with coefficient of polynomial, explain geometrical meaning of zeros of a polynomial. Let us start our discussion with some examples of polynomials. Polynomial is a mathematical expression with a variable and a constant term, and it is denoted by p of x. Degree of a polynomial is the highest power of variable in any polynomial term. The degree of first polynomial is 1. The degree of second polynomial is 2, because variable x has highest power of 2. Similarly, the last polynomial has degree 3 because the highest power of variable x is 3. Based on the degree of polynomials, polynomial is classified into 3 main types: linear, quadratic, and cubic. A polynomial of degree 1 is called a linear polynomial. These are some examples of linear polynomial. Its general form is ax plus b. A polynomial of degree 2 is called quadratic polynomial. These are some examples of quadratic polynomial. Its general form is ax square plus bx plus c. A polynomial of degree 3 is called cubic polynomial. These are some examples of cubic polynomial. Its general form is ax cube plus bx square plus cx plus d. This is the general form of a linear polynomial. A real number k is said to be 0 of a polynomial p of x if p of k is equal to 0. For this linear polynomial, ak plus b is equal to 0. Hence, k is equal to minus b upon a. This is also equal to minus of constant term divided by coefficient of x. Let's find out this relation for quadratic polynomial. Consider alpha and beta as zeros of a quadratic polynomial. P of x is equal to ax square plus bx plus c, where a is not equal to 0. Then x minus alpha and x minus beta are factors of polynomial of x. So, ax square plus bx plus c is equal to k times x minus alpha into x minus beta. Here, k is a constant. Upon simplifying, we get ax square plus bx plus c is equal to kx square minus k alpha plus beta of x plus k alpha beta. Now, upon comparing both the sides, we get a equal to k, b equal to minus k into alpha plus beta, and c is equal to k alpha beta. Upon substituting k as a, we get alpha plus beta as minus b upon a. Hence, sum of zeros is equal to minus of coefficient of x upon coefficient of x square. We get alpha into beta as c upon a. Hence, product of zeros is equal to constant term upon coefficient of x square. Let us understand these relations by solving a problem. Let's find the zeros of polynomial x square plus 7x plus 10. X plus 2 and x plus 5 are the factors of this polynomial. Hence, if p of x is equal to 0, then x is equal to minus 2 or x is equal to minus 5. Hence, the zeros of this polynomial are minus 2 and minus 5. Now, let's verify the relationship between zeros and coefficients. Sum of zeros is equal to minus 7 upon 1, which is equal to minus of coefficient of x upon coefficient of x square. Product of zeros is equal to 10 upon 1, which is equal to constant term upon coefficient of x square. If alpha, beta and gamma are the zeros or roots of a cubic polynomial, ax cube plus bx square plus cx plus d equal to 0, then sum of zeros is equal to minus b upon a, which is equal to minus coefficient of x square upon coefficient of x cube. Product of zeros is equal to minus d upon a, which is equal to minus constant term upon coefficient of x cube. Sum of products of zeros taken two at a time is equal to c upon a, which is equal to coefficient of x upon coefficient of x cube. We can't give an exact definition or meaning of zeros of polynomial without geometrical representation of polynomials. Let us represent a linear polynomial y equal to 2x plus 3 on a graph. To represent any linear polynomial on a graph, we require at least two coordinates. We will choose any easy value of x and try to get the corresponding of y. Upon putting value of x equal to minus 2, we get y equal to minus 1. Similarly, upon putting value of x equal to 2, we get y equal to 7. It is clear that graph of y equal to 2x plus 3 is a straight line. This straight line intersects x-axis at coordinate minus 3 upon 2 and 0. We can observe that 0 of 2x plus 3 is minus 3 upon 2. Thus, the 0 of a linear polynomial is the x-coordinates of the point where the graph of polynomial intersects x-axis. The linear polynomial has exactly one 0. Now consider an example of a quadratic polynomial, y equal to x square minus 3x minus 4. We will try to find the different values of x and y which is satisfied by this quadratic equation. The first such pair can be x equal to minus 2 and y equal to 6. Similarly, there are different values of x and y. This is the shape of the graph we get for this quadratic equation. If the coefficient of x square is greater than 0, like in this case, the shape of the quadratic polynomial is upward. If the coefficient of x square is less than 0, then the quadratic polynomial is downward. From the graph, we can see that this graph cuts x-axis at minus 1 and 4. Hence, the zeros of this quadratic equation are minus 1 and 4. There are three cases for quadratic polynomial. These cases depend on where the graph of polynomial intersects the x-axis. When graph of a quadratic polynomial cuts x-axis at two distinct points a and a dash, then the x-coordinates of a and a dash are two zeros of the quadratic polynomial. When the graph cuts x-axis at one point, then the quadratic polynomial has only one 0. When the graph is above or below the x-axis, then it does not cut x-axis, and hence there is no 0. Geometrically, it is clear that each quadratic polynomial has two distinct or equal zeros or no 0. Now consider an example of cubic polynomial y equal to x cube minus 4x. Let us choose values that satisfy x and y in this equation. From graph and table, zeros of x cube minus 4x are minus 2, 0 and 2. Let us consider more examples of cubic polynomial. For polynomial y equal to x cube, 0 is only 0 of x cube. For polynomial y equal to x cube minus x square, 0 and 1 are only zeros of x cube minus x square. From these examples, it is clear that there are at most 3 zeros for any cubic polynomial. In general, given polynomial p of x of degree x has at most n zeros.